Hi, kids. This time we are going to do an incline problem. So we're going to have a box. It's sliding down an incline. It's sliding at a constant speed. And you have to figure out the force of friction and the normal force. Okay. So let's think about this. What do you think is going to be your first step in solving this problem? Oh yeah, what's your first step? Always to draw your picture. So we are going to draw a picture to represent this. Now, when you draw your FBD in this case, you are going to draw it big. Okay, I do not want you to do something like this. Okay, so there's there's my box. No, you are going to draw a big FBD, okay? Where this is 20 degrees. Here is my large box on an incline. Okay? You make it nice and big, especially the first time through. It's going to be way, way easier to see things. Okay? All right, so let's go through. So, what forces are acting on this box? Let's see. Well, there's gravity acting on this box. So, which way does gravity pull things? Gravity pulls things straight down. Duh. So let's draw the force of gravity going straight down. Now I'm going to draw this force big, okay, and I'm going to label it the force of gravity, okay? What other force is acting on this box? Well, that means the normal force is acting on this box. So the normal force is going to be pointing that way. Why? Because the normal force points perpendicular to the surface. So make sure that if there's my surface, okay, do you see how that is at a right angle? Okay, so make sure when you draw it at a right angle. And then, what else is there? Well, it's sliding down the box, down the incline so that there's friction. So that means friction is going to be pointing this way, up the incline, okay? So in this case, there's just those three forces. Does that mean there's only going to be those three forces? Of course not. You know, if there's a hot air balloon attached to it, it would be pulling straight up. You know, if you're pushing it, could you have an applied force? But in this particular problem, that's what you have, okay? So, it is moving at a constant speed. What does that mean? That means there's no acceleration. That means if you add these three forces up, you should get 0. Okay. Now, if you wanted to, we could do this. And I'll just show it to you. If I was just adding them tip to tail, I am going to get that. Do you see that? Normal force, force of friction, force of gravity. Hey, look, I end up back where I started. My net force would be 0 as long as I drew it correctly. Okay. Now, in this particular problem, though, if you look, okay, this box is moving this way. Okay, it's moving parallel to the incline. So then I still have to break a force into its components. This is perpendicular to the incline. This is parallel to the incline. This is neither. So this is the one I have to break into its components. So I'm going to strongly recommend to you, draw your perpendicular component of gravity first. Why? Because the perpendicular component of gravity has to point exactly opposite of the normal force. You see that? See how that's a straight line? Isn't that nice? And then draw your parallel force down here where this is your right angle. Now, I have students that do this, so you can kind of check yourself, okay? I'm going to draw it over here. This is one of the most common mistakes I get. So I have students that go like this. They go, well, I have this force and then this force, okay? No, this is not parallel to that. Do you see that? Or the other way to think about this, guys, gravity is going to always pull things down. Do you see how this component has a downward part? This component has a downward part. This, if you drew it this way, this is horizontal. That doesn't really make sense, okay? So you're not going to draw that. So check your picture when you do this. This and this have to be parallel to the surface. This and this are perpendicular to the surface. So it's really super duper important that you draw a good picture. And then let's label this. This would be FG perpendicular. and then this would be FG parallel. Okay. Now, I'm going to do my next step, which is going to be to write my two equations, because again, I have perpendicular forces, I have parallel forces. So if I write my perpendicular force equation, well, it would be this one and this one are perpendicular, so I'd say Fn minus Fg perpendicular equals 0. So look, remember when we talked about this? The normal force is not always equal to the force of gravity. This is another example of the normal force not being equal to the force of gravity. In this case, the normal force is equal to this part of gravity. And then if I, just so, I'm going to write it two separate ways, because again, you could write it like this, or you could write it like this, just so you can see it. This would be, well, this minus this, or this minus this. It doesn't really matter. I'll just say FG parallel minus FF, and then that equals 0. Okay? Now, does this always equal 0? It does. Why? Because it's never ever going to accelerate into the surface or off the surface. Does this always equal 0? Of course not. Why does it equal 0 in this particular case? It's because it's moving at a constant speed. Okay, the acceleration is 0. If it was accelerating down, then you would say equals ma. Okay, if it was accelerating up the incline, which could happen because if friction was really, really strong, then you would write FF minus FG parallel equals ma. Okay, so it's this is 0. Why? Because in this particular problem, it was moving at constant speed. So FPD, equation. Now we have to go about plugging our stuff in. So this is one of the reasons we made our diagram super duper big. I want to show you something here. So if you look, okay, at this red triangle, okay, 20 degrees, 90 degrees, 70 degrees, okay, using my mad trig powers, okay? Or actually, this would just be my mad geometry powers. Well, if you look, if this is 70 degrees here, this angle right there also has to be 70. Does everybody see that? This angle and this angle have to be 70. Well, this is 90, which means this top angle is 20 degrees. Does everybody see what I did there? So again, if this is 70, this itty bitty one here is 70. That has to be 90 because it's perpendicular. So this top angle always is going to be 20 degrees if you draw it this way, which is another reason why I would like you to draw the perpendicular first parallel that way. But hopefully that makes sense that this is going to be that. It's essentially similar triangles. You know, if I took this triangle and I turned it, okay, you can see that this triangle and this triangle are similar to each other. Okay, so now let's plug our stuff in. So, well, FG perpendicular is going to be, if you look, that's adjacent to it. Does everybody see that? So this would be, and if you don't see it, just think about it this way. So like cosine of 20 would equal adjacent FG perpendicular over FG. So which means FG perpendicular equals FG times cosine 20. So in this case, it would be 60 times 9.8 times cosine of 20 equals 0, and then I can solve for the normal force. And if I do that, 60 times 9.8 times cosine of 20, I get 552.54 newtons. And in this case, it would be pointing kind of like that way, okay? On this side, okay, it would be, you know, again, if I'm talking about this side, well, that would be if you think sine 20 equals FG parallel over FG, that would mean this is going to be 60 times 9.8 times the sine of 20 minus the force of friction equals 0. So 60 times 9.8 times the sine of 20 that would be my force of friction equals 201.1 newtons, and it would be going kind of parallel up the incline. Okay, so hopefully that makes sense. The last thing I just want to mention, this idea of finding friction because something is moving at a constant speed is going to be super duper duper important to you. So just keep that in mind that, hey, look, if these are the only forces acting, we can find the force of friction, because that means in labs a bunch of times you're going to be getting things moving at a constant speed. Why? So you can find the force of friction. Okay, bye kids!